In this paper, we present MOVIS, enhancing multi-object novel view synthesis for indoor scenes. Given a single-view image capturing multiple objects and the relative camera transformation, MOVIS generates plausible and high-quality target view images. Apart from Objaverse, MOVIS can also generalize well to diverse unseen images, including samples from YouTube videos, 3D Front, Real Estate 10K, Sun RGBD, and ScanNet++. We also visualize cross-view matching results using image matching techniques. Compared with baseline, MOVIS can match a significantly greater number of points, closely aligned with the ground truth. Current novel view synthesis models primarily focus on single-object scenarios, demonstrating strong 3D-aware generative priors for individual object generation. However, it remains unclear whether this paradigm can be effectively extended to multi-object level to facilitate more complex tasks like indoor scene reconstruction. We start by directly applying current off-the-shelf NVS models to multi-object scenarios. Given an input view image and relative camera pose change, we visualize synthesized results of 0, 1 to 3 on the right, as well as the ground truth reference image on the left. Our observations reveal that current NVS models struggle with multi-object scenarios. They fail to accurately predict global attributes, such as object position and orientation, and may even lose track of objects under novel views. Additionally, at the individual object level, they often produce implausible geometries and appearances. Therefore, we propose MOVIS, a novel view synthesizer aiming to handle multi-object composites. Our model builds upon a pre-trained image diffusion model, Stable Diffusion, and repurposes it as a novel view synthesizer by incorporating camera pose change along with image feature. From the motivation that a multi-object NVS model should first grasp hierarchical structures, including high-level object placement and low-level details within a single view image, we inject structure-aware features, object masks, and depth maps of the input view as additional inputs to the model. Additionally, we utilize the prediction of novel view object masks as an auxiliary task during training to enhance the model's capability to differentiate object instances, laying a solid foundation for fine-grained geometry and appearance recovery. Before diving into the detailed design of our structured guided time-step scheduler, we visualize the sampling process of diffusion model. We find that larger time steps emphasize global placement learning, including object position and orientation, while smaller time steps focus on detail recovery, including object geometry and appearance. Therefore, we propose a structure-guided time-step sampling scheduler that prioritizes larger time steps in the initial stage of training while gradually decreasing over time to balance global placement learning and local fine-grained detail recovery. To facilitate the training and evaluation of our proposed method, we curate a scalable synthetic dataset comprising 100K scenes for training and 5K for testing. Apart from testing our model on the in-domain dataset C3DFS, we also perform generalization tests to unseen datasets and images, including room texture Objaverse, 3D Front, Sun RGBD, ScanNet++, Real Estate 10K, and YouTube video images. Our method generates plausible novel view, surpassing baselines regarding object placement, shape, and appearance. We also visualize cross-view matching results. Points of the same color indicate correspondences between the input and target views. We achieve a higher number of matched points with more precise locations. We visualize continuous rotation results of our model. Our model is capable of synthesizing both occlusion and occluded content under novel views. Our method can not only synthesize new occlusions under novel views like the wardrobe and the sofa, but is also capable of synthesizing originally occluded objects under novel views. One downstream task of our model is the capability of deleting an object under the novel view, thanks to the synthesized mask image. We remove objects under novel views simply by thresholding the predicted mask image. Another downstream task is reconstruction using the synthesized images. Given an input view image, we rotate the camera around these multiple objects to acquire multi-view images. We then apply DUS3R for feed-forward reconstruction of the scene. To sum up, in this paper, we introduce structure-aware features as model inputs and incorporate novel view mask prediction as an auxiliary task during training. This enhances the model's understanding of hierarchical structures in multi-object scenarios, leading to improved NVS performance. We present a novel noise time-step sampling scheduler to balance the learning of global object placement and fine-grained detail recovery, which is critical for addressing the increased complexity in multi-object scenarios. Through extensive experiments, our model demonstrates superiority in consistent object placement, geometry, and appearance recovery, showcasing strong generalization capability to unseen datasets.